Hi everyone, my name is Hoàng Nhân Lưu from the Hong Kong University of Science and Technology. Today I would like to discuss one of our most recent work, namely the Axi-Higgs Cosmology. I will give the first part of the talk, and my collaborator Lingfeng Li here will give the second part of the talk. To start, we know that in cosmology, there are a lot of tension emerging recently within the ΛCDM paradigm. Most notably is called H0 and SA tensions. So if we look at this plot right here, we will see that the prediction from ΛCDM actually give SA's value about 2 to 3 sigma higher than some value inferred from the weak lensing measurement from some experiment like kits. While at the same time, it also gives H0 4 to 5 sigma lower than some local measurement using cosmic distance ladder like SHU. So even though there's a lot of debate that whether there's some uncertain systematic within these experiment, we take the standpoint that ΛCDM by itself needs to be modified. So we're trying to do that by increase H0 and also trying to decrease SAs by some mechanism. So to do so, we would like to introduce a model called Axi-Higgs. So in our Axi-Higgs model, the Higgs wave is driven by the axion field. So if I denoted the Higgs wave as V, I can decompose it into V0, which is some base value, and delta V, which is a deviations. So if I choose V0 as 246 GeV, which is the value that we measure for the Higgs wave nowadays, then my deviations will be dependent on the axion field A. Here, C and M Planck is just some constant. So this delta V is driven by the axion field A. The axion field A by itself is involved following some standard misalignment mechanism. By the sense that at first its density will stay constant, just like dark energy, and at late time it will behave like dark matter and leave some relic density at the present day. So Axi-Higgs model essentially introduced some extra parameter. However, for my purpose in cosmology, I just take omega A and delta V as two most important parameters. To demonstrate how our model works, here I have the deviation of the Higgs wave as a function of time. So at first, it will stay constant because the axion field stay constant. And then up to some point after recombination, it will start to drop diluted and start oscillating rapidly. So the reason I want this setup because I want the Axi-Higgs model to resemble ΛCDM with the higher wave of the Higgs field before recombinations, while after recombination, the Axi-Higgs model just resemble ΛCDM with some axion dark matter. So what is the implications of the Axi-Higgs model? So first, it will modify recombinations. If I have the Higgs wave increases before recombination, it essentially increases the mass of electrons. And when the mass of electron increases, it makes electron recombine faster. Here, to illustrate that point, I have a plot of Xe, which is a free electron fractions over time. So if I have the black curve here denote at the standard recombination curve of the free electron fractions, I will have the red curve is the case where the ME is increases. So as you can see, the recombinations of the red curve happen earlier, and so it dropped earlier than the black curve. So if we have the electron recombine faster, essentially, we will make the recombination happen earlier. And so we will increase the recombination redshift denoted as Z star here. When we increase the recombination redshift, we reduce the cell horizon to recombinations because R star is just by definition integral of Z star to infinity. And to maintain the CMB structures, we want to keep this theta star value fixed because this theta star is tightly related to the first peak of the CMB spectrums. To keep theta star fixed and R star decrease, we also need to decrease D star. And to decrease D star, from its definition, we can see that we have to increase some energy budget in the universe at late time. Essentially, we need to increase either omega m, dark matter in general, or dark energy. And so by increasing either of them or increasing both of them, we're essentially increasing Hubble value. And this is the key point to resolve the Hubble tension in a lot of models, as well as in our model. Axi-Higgs also modified the structural formation after recombination because essentially at this time, axions behave just like dark matter. However, they still have some fundamental difference. So as you can see on the right-hand side here, I have the total matter power spectrums. And so if I increase the axion fractions within the total matter, denoted as F, the more axion I put in the universe, the more structure is suppressed, of course, under some scale. And this scale is usually related to also the axion mass. Here, this plot is for the axion fuzzy dark matter of about 10 to the minus 22 eV. However, it will also apply to our Axi-Higgs axion, which is about 10 to the minus 29 to 10 to the minus 30 eV. And this is the key point to resolve the SA tension because actually the suppression of the matter power spectrum is also suppressed SAs. So finally, we will come up with this constraint from the Axi-Higgs model. This is a plot I showed you in the first slide of ΛCDM. Now, if I have the Axi-Higgs model added in, we will see that the contour preferred by Axi-Higgs is overlapping with both experiments. So Axi-Higgs can resolve both tension at the same time. On the right-hand side, I also show another figures, which is to show that in the Axi-Higgs model, this is ΛCDM, Axi-Higgs actually have lower cell horizon than ΛCDM and also a higher H0. And finally, I would like to draw your attention to some other well-known problem that the Axi-Higgs model can address, like the lithium puzzle for BBN. Here, as you can see here from this panel, where the relic abundance of the lithium-7 is significant from the astrophysics measurement is significantly lower than the standard value predicted by BBN. And it can also potentially explain the recently discovered isotropic cosmic birefringence. So essentially, because of the axion field exists, it may also interact with the photon field and it will change the polarizations of the photon in some non-trivial way. And it also has some impact on the quasar spectrums and some atomic clock measurement that will be discussed in the next talk by my collaborator Lingfeng.
So in this section, I will talk about some very important but rather unaddressed parts of cosmology impacts of our Axi-Higgs model, namely BBN, isotropic cosmic birefringence, and also how possibly we can detect it, and if we have or not, and what happens in the future, and then summarize. So let's go back to BBN first. So BBN is an era where all the nucleons forming heavy nuclei with like the temperature scale around MeV-ish. So if we want to be serious about our Axi-Higgs model, then we must go back in time because the Higgs wave is also raised at that time and it undoubtedly affects nuclear synthesis. And if we want to survive, then we want to deduce or like say figure out the impact on BBN of a raising Higgs wave. Of course, this can be very non-trivial. So even if we look at the most simple, the simplest ever measurable observable at that era, the N/P ratio is controlled by so many parameters. any of these parameters can be written in a very complicated way. But overall, if we want to write down the impact of the increased VEV, there are four major impacts. First of all, is the increase of the W mass, and therefore the Fermi constant becomes less. So this affects all weak interactions because essentially the weak interaction goes through the charge current dominantly. And this affects the N over NP conversion or equivalently neutron synthesis and also neutron decay. Electron mass in this case is doing the same role. We are not forming atoms yet, so the electron is just going to mess around with proton and from neutron and vice versa. So the effect would be similar. So as the so-called isospin breaking effect, recorded as the light quark mass differences, this would also proportional to the Higgs VEV. But overall, for all these electroweak processes, actually we have good control because in principle they can be calculated like in perturbative orders, and we know pretty well even with an increased Higgs VEV what could possibly happen. So the effect would be moderate, but when the average light quark mass right here, MQ bar comes into play, everything becomes different because that's how nuclear physics come into play. And essentially, an increased VEV increasing the light quark mass increase the M pi, because from chiral perturbation theory, we know that M pi at the leading order is proportional to the square root of light quark masses. So just from this plot that we just know, because the change of the pi masses and all the subsequent changes, the heavy nuclei, say lithium-7 and its prototype, like say beryllium-7, and also all the heavy nuclei is actually pretty sensitive to light quark mass ranges, like say more sensitive than helium-4 and all the remaining light elements that they need to combine and synthesis heavy nuclei. This is because the pi becomes massive and the binding energy of the heavy nuclei just becomes less, especially when you need to go over the Coulomb repulsion. To summarize, we actually put and calculate the different effects like of electroweak physics and also light quark mass right here. And we see that the most significant effect actually comes in with the light quark masses, while all the remainings are moderate. And by doing so, we actually can make sure that we are compatible with the current very stringent constraint on helium abundance and also neutron, but also reaching a significant reduction of the lithium abundance. Therefore, we close the gap between theory and observation. At the end of the day, we do the fit of the BBN. So we find that the preferred regime is the delta V at the BBN error should be of 1%, while the baryon to photon ratio or equivalent omega B increased by 1 to 3%. But in this sense, we are compatible or overlaps with the CMB preference. So that's okay. So let's move on to the next part, the ICB effect. So it is a very general story, and it happens when you try to write down a theory of an axion, especially when this axion coupled to standard model. In this case, we couple to Higgs. So inevitably, such kind of coupling at one loop order or tree level, it comes in. If we're gonna write down this way, this is just the most common formalism, then we define the scale Fa, usually considered as the axion decay constant. And since this is a CB-odd coupling, so and naturally breaks parity because we have no idea, like say the initial phase of axion is it positive or negative. So when you start to roll from the initial value, we introduce a parity breaking effect and start to rotate the polarization plane of CMB photons. And well, it can be simply written this way. So initially, before the recombination finishes, it stays at the palato, and then nowadays, after millions, billions years of damping, it goes to 0. And we finally simplify the equation into this way. As long as we believe or trust this reanalysis result of CMB that beta angle is like this 2.4 sigma from 0, then we can easily go to conclusion that A over A initial over FA is a very natural number around 1. This must be true for all our benchmark mass. And we finally get the very natural number, so no need for fine-tuning. We come to the final point, that how possibly we can observe since these axions coupled to standard model and they have a significant impact on our real life. So unfortunately, since though there are so many axion searches around, but they are focusing on much heavier axions with much higher frequency, our benchmark, remember that our benchmark model has 10 to the minus 29 EV, so that's like by far in any reach of like a ground-based experiment in any future. But still, luckily, we can still monitor the annual drift of constants, like say right here showing the electron to proton mass ratio, or effectively just delta V to a very good approximation. Or we can find them in a very distant past by looking at the sky. So in terms of annual drift, the current best results actually coming from atomic clocks by measuring some very heavy atoms and their frequency differences in different modes. So by a time span of around 10 years, such experiment, the latest result give you the constraint on such the drift mode, that delta V can change by, say, order 10 to the minus 17 per year. So this immediately gives you the constraint of axion to be 2 times 10 to the minus 30 EV. But of course, this is by far any real constraint to our model, because our target or our benchmark actually around 1 to 3 times 10 to the 29 EV. So in order to make some real progress, we need to go 1 orders of magnitude greater, or 1.5, reaching this 10 to the minus 18 per year level. This actually requires some fundamental improvement of these atomic clocks, and eventually we may go to nuclear clocks to be more sensitive to the quark mass changes. But we expect that there could be some breakthrough in the next 1 to 2 decades, given the fast progress in this field. We can also looking for the deviation in distant past, because the further you go, because the axion oscillation actually damps itself. So the further, the higher Z we observe, the more likely we can observe some deviation. And that this is possible by observing molecular spectral lines in quasars, some very distant but very bright object. We must go molecular because the different modes in a molecule, say rotational modes, vibration modes, are different from the electronic transitions. Therefore, we can break the degeneracy between delta V and the redshift. And so far, we summarize different measurements right here. They are all, I mean, to the time that we published, these are all available measurements. But unfortunately, we see that even for the 1 to the minus 30 EV case, we cannot make real constraints. So we need to wait for the next generation experiments. So we just here a quick summary. So I'm just throwing 2 plots right here. So first one showing that the marginalized posterior of different cosmological parameters given different benchmark masses, and so far they are all good. The second plot shows that the different pieces of evidence just coexist perfectly each other in this regime. So in brief, just a take-home message for our Axi-Higgs model, how it works is just a higher Higgs VEV during the recombination time and earlier, because the heavy electron mass bring you an early recombination, and therefore a higher Hubble is allowed. And also it is compatible with the current BBN observation, and it potentially gives you the solution to the lithium-7 problem. On top of that, going to an axionic solution is going to buy you the answer to the sigma 8 tension, usually brings the early recombination solution less preferable, but here it naturally solved in our model. It gives ICB, non-zero ICB for free almost. It is just an innate feature of the theory, and also it grants us great accessibility in future observations. So thank you.